Alright, hi everyone. This is today's session is about 9A and 9B. It's introduction to differential equations by using the technique of uh, differentiation and later on anti-differentiation. With 9B, we'll look at solving different differential equations. This time we're going to use a function with an independent variable. Here that's going to be x. A differential equation will be an equation. It will contain derivatives of a particular function or variable. Using integration method, you can find a general solution, but you will need more information if you want to obtain a particular solution. So remember, a general solution, when you anti-differentiate, it will be a plus constant that you do not know the value. You can also verify a solution through substitution. We'll do an example in a second. And to the additional information, we may use a different notation. So if you call y a function of a variable x, if we annotate y comma 0 equals 3, what it means is if you substitute x equals 0, the y value is equal to 3. So with the first example, just go have a look through the textbook, have a look at example 1, 2, 3. I'll stop with this one with example 4. It's you need to find two values a and b. So the idea is using resolving simultaneous equations. Here in this situation will be linear. You have a function y, and what you need to do is you have a differential equation that will include the y function, which is defined above, the first derivative, and then the second derivative. So you will have to do two differentiation and substitute into your equation and solve for a and b. You have your y function, you do the first derivative, you use a product rule. We'll see that in methods. You'll simplify and probably leave it factorized. That's fine. It's another product function. So when you differentiate again, you apply again a product rule, and you end up with this function. So have a go at that working out. Probably in the way. So if you were here, as I was saying, this is going to be your second derivative. So you're going to use the first derivative and the second derivative and substitute into your equation. So after you substitute, you have your second derivative. Yeah, that's your equation. You have your second derivative, first derivative, and your y function. You substitute into here. Now notice you have a exponential e of 4x as a common factor for all of it. Knowing that it is always positive, what's important is not equals 0, is we can factorize and simplify. You end up with this equation. We regroup the like term in x and the constant term, and that whole expression needs to be equal 0. What it implies to be all independently of x to be equal 0 is both factors have to be 0. So the first coefficient is 0, the second coefficient is 0. That gives you two equations in terms of a and b, linear equations. We do an elimination method. We determine the value first, the value of a, we substitute into one of the two equations, and we get the value of b. Alright, so with 9b, you get a differential equation. So the first derivative is equal to a function, and what you need to do to determine the original y function, you need to apply the integral and then anti-differentiate. That will give you a general solution. Example 5, it's about applying what you've learned in the previous chapter. So it's anti-differentiate some functions. The way it's set up is as a differential equation. So the first derivative is equal to an expression, and which is a rule that you need to anti-differentiate. Here, different notation, so it's dy over dx. For b and c, it's an expression in terms of dt. And the last one, notice they just swap around the variables. So it shouldn't be an issue. You anti-differentiate in terms of y, but the function on the right hand side is also a function of y. Okay. If just pause the video, have a go at those examples yourself. Okay, and then I'm just gonna move on to the example one at a time. All right, so with example A, it's a polynomial expression. So you anti-differentiate using the rule for power functions, and you obtain this rule. Don't forget you have a plus constant. With part B, so dy over dt is sine of 2t. You anti-differentiate. It's a chain. Apply the chain rule or do a temporary substitution. If you're confident with that, you have a 2 coefficient, so it's going to be a 1 over 2 here. The antiderivative of sine is negative cos, and you obtain this rule plus constant. Here with the next one, C, e of negative 3t. So again, it's a composite function. You need to have that negative 3 factor becomes a negative 1 over 3 of exponential. 1 over t is log of e. When you apply the log of e, don't forget your modulus, because you don't know the restrictions on the domain for t. And don't forget your constant. Alright, so over here you need to anti-differentiate in terms of dy, which what we done over here. It should be familiar using the inverse circular function. It's an inverse tangent. It's in terms of y, and if you wanted the expression in terms of x, you will have to rearrange it to make y the subject, and you end up with this expression. Again, there's a constant, so you're not too sure, you don't know the value of it. You can also solve differential equation using a specific function on a CAS calculator. So if you're on the calc page and you select menu, calculus, differential equation solver, which is a differential DE differential equation solve, you write your whole equation. Okay, notice the symbol, it's a prime for the first derivative. Because you're going to specify the two variables, it's going to be the derivative in terms of x, and you have an expression in terms of x. Okay, so it's under the pi button. You will have a menu with that symbol available to you. Okay, vice versa, you can also have a dx over dy, but the expression will be a function in terms of y, and you will swap around the variables. So don't forget the order of the variables matter. Okay, and yes, it did create your constant. Notice also it will if you want to rearrange it in terms of y, you can use a solve function. It will restrict the domain, so the function is a 1-to-1. With 9b, so just before we go to the algebraic resolution, when you have a function in the terms of y prime equals x, if you do remember, it's a polynomial, so it's order 1. The antiderivative will be half of x squared plus a constant. Because it's a plus constant, you end up with a whole formula depending on the value of the constant. So that constant is k. Depending on that value, you can see that all the curves are just variations of vertical translations. Okay, that's for the y function. As you have an infinite number of members for that family, to get that particular solution, you need to specify a point or a certain value. So here it's 4, 2. You substitute those values into that equation. That will give you the value of k. So you can only have now a unique parabola that will go through that point. So those conditions, 4, 2, I say conditions plural because we'll see when we do look at differential equation, it can involve the second derivative, and if you have the second derivative, you anti-differentiate once, you get one constant. If you anti-differentiate again, you will get a second constant. So you have two constants, two unknowns. You will need two conditions to be able to find the unique solution for that particular equation, which is what we have here. So you will have to anti-differentiate twice to get the y function. And we'll look at example 7. So with this example, again, there's 4 parts. Attempt those questions yourself by pause the video and have a go at anti-differentiate twice. Now, as it is a general solution, you don't have to worry about the values of those constants, which is a reminder to every time to anti-differentiate to have those constant to your general solution. With the first one, so you have the second derivative, that's a polynomial, so you will need to anti-differentiate once. So we anti-differentiate once here, that's fine. So you follow the working out, which is your derivative. Then what we do, we need to anti-differentiate again. And notice that c constant, when you anti-differentiate, become a linear term, so it's cx, and you will have to add a constant because you anti-differentiate that second time. Alright, part B, an easy circular function that is linear. You will do the first derivative is sine of 3x. Don't forget it's a 1/3. Again, it's a chain rule because you have a composite function plus a constant. So that will be the expression of your first derivative. And what you would need to do is anti-differentiate again. So it will be, because it's a sine of 3x, it will have a 1/3 here times the 1/3, that gives you 1/9, and the antiderivative of sine is a negative cos. The c constant, when you anti-differentiate, will become a linear term, so cx, and you have anti-differentiated, so you will have a plus d, which is your constant. Next. Second derivative is e of negative x. It should be pretty straightforward because do remember the e of x, when you differentiate is itself. As you anti-differentiate e of negative x, it's a composite function. You will, every time you anti-differentiate, you will introduce a -1 factor. So the antiderivative of e of negative x will give you negative e of negative x. As you anti-differentiate again, it will go back to its original because you multiply the negative e of negative x by negative 1, which is here, but you have a constant term that you anti-differentiate that gives you a linear term plus constant. Alright, second derivative is 1 over square root of x plus 1. If you had an x squared and we have a negative, you can think of the inverse circular function. In this situation, try first always think about a polynomial. So here, to do that as a polynomial, you could have done a temporary substitution by calling x plus 1 u and bring it to a rational power, which is negative 1 over 2. As you get more experience, you will notice that in that situation, if you have u equals x plus 1, because you have a 1 coefficient in front of x, if you do du over dx, it equals to 1. So that shouldn't, by doing that substitution, you can probably do it mentally. So let's say we leave it as it is. We follow this working out. As we anti-differentiate, we plus 1 the this one, we plus 1 the power, that will become a positive, so that's a 1 over 2, and we need to divide by 1 over 2, that gives you a 2 coefficient. Still a polynomial, you have a plus c here, that inside your integral, you anti-differentiate, you add 1, that gives you 3 over 2, so you have a 3 over 2, it means you need to have a factor 2 over 3, that gives you times 2, 4 over 3 here, plus cx plus constant. Alright, with last example, so part A shouldn't be, it's the straight steps that you have done before, is you find a general solution, you will have two unknowns, so your c and your d, and to find their values, part B will give you two conditions, so you will have a value for the first derivative and then the value of the y function. So let's get started with finding the general solution. So you have that second derivative equals a cos squared, and I would pause the video and attempt to anti-differentiate first and a second time. Alright, let's continue. Your second derivative is here. To find the antiderivative, it's the integral of cos of square. The power is square. You need to use your dual angle property of cos of 2x. So you would use that when you have a cos squared or a sine squared. You replace that by that cos of 2x. So it's a nice linear expression that you can anti-differentiate. The cos of 2x will become half of sine of 2x. The half times with the half will give you a quarter. We need to expand that term. That gives you a plus a half, which is plus a half x when you anti-differentiate, plus your constant. So that's your general solution for the derivative. Then we anti-differentiate that derivative, so that is the expression. Sine of 2x, the antiderivative is negative 1 over 2 cos of 2x. That'll give you this first term. Here it's a x, so that's a half of x squared. That gives you a quarter of x squared. C is cx, and you have a plus d. So this is your function y. Okay? And that is the general solution. Now, for part B, you have the derivative here. That y of 0, we're going to use this expression, but for the derivative of x equals 0 equals 0, we're going to use the previous expression, which is this one. And what we'll do is we'll get the C value, which we will place into here, and then you will continue the solving. So let's do this. So we have the expression of y. The first condition is the derivative of y in terms of x is equal 0 when x equals 0. So we have dy dx. We substitute x equals 0 and y equals 0. That gives us c is equal 0. So the cx term disappeared. That gives you the simplified form of y. D is the only unknown. We rewrite this, and we substitute x equals 0 and y equals negative 1 over 8. That gives you an expression, and d equals 0. So the simple solution now, the unique solution of that function is given over here. Okay, and that's the end of this session. See you.